Myself, Dr. JIBRAN Ahmed presents to you Simply Pathology, and today we are back with a very important lecture. Today we are going to understand the approach to hereditary hemoglobin disorders, part 2. In the previous lecture, we had done till electrophoresis, and in today's lecture, we are going to start with HPLC. Now, HPLC is a very important concept to understand in the post-graduation. Why? Because a long answer question is asked. You will be getting certain charts, okay, on HPLC. So it is very important to understand the basic principle. In today's lecture, we will understand basically what is HPLC and how it is working. And in the next lecture or in the subsequent lecture, we are going to see certain important HPLC charts and its interpretation. I will teach you the basics today. Okay, so let us begin. So what is the full form of HPLC? It is called as high performance, high pressure liquid chromatography. So why is it called so? We will discuss that in this particular part only. So if you see, this is basically liquid chromatography. Or what is chromatography? Basically in this method, if you see, if there is a solution that is containing many different types of hemoglobin or any different types of molecule. So by this process, what they are going to do, by this process, they are just going to separate, okay, the different hemoglobin variants, okay, including the normal ones. So it can be used for separation of many other entities, but over here in hematology, we are concerned only with the separation of different kinds of hemoglobin variants. Okay, so this is what we are going to learn. This is what happens in case of HPLC. Now, this technique, before I come to the technicalities and how HPLC is working, first let me make you understand that this technique is used as a screening test for detection, identification, and not only the identification but the quantification of the hemoglobin variants. It is also used for the quantification of HbA2 and HbF. It is also well suited for neonatal screening because it requires a very small amount of hemoglobin and needs a small amount of blood. So for pediatric population, HPLC is highly suited. Now, various automated HPLC systems are available. It is also used for quantification of HbA1c for monitoring diabetes mellitus. Now, for those of you who don't know, HbA1c is the glycated form of the hemoglobin. And it is not only used for monitoring the progress, but nowadays it is also used for diagnosis of diabetes mellitus. Okay. Now, automated cation exchange HPLC is being used increasingly as the initial diagnostic method for diagnosis of hemoglobinopathies, okay, in laboratories which are having a very high workload. So as I told you previously, that one of the limitations of electrophoresis is what? The limitation is that by electrophoresis, you cannot carry out when the sample load is very high because it is a labor intensive work. Okay, so both the capital and consumable cost are higher as compared to hemoglobin electrophoresis, but the labor cost is less. So what happens that with HPLC, if you see, the overall cost becomes very much similar to electrophoresis. So why not go for HPLC? Because HPLC is far more better as compared to the electrophoresis. Now there are four major advantages. Some of them I've already discussed. So the analyzers, they are automated and they require less staff time and they permit more processing of larger batch. So you can sample a larger amount of sample, with a very less amount of labor in a very short time. So this is very time saving, okay, and it is, highly automated. So less labor intensive it is. Now, very small samples, approximately just 5 microliter of blood is sufficient for analysis. So it is very much suitable for pediatric work. Now, quantification of the normal hemoglobins, that is the HbA2, FA, they can be done. Along with that, variant hemoglobins are also available on every sample. So you can do, you can carry out all the different kinds of quantifications, okay, of the normal as well as the variant hemoglobin. A provisional identification of larger proportion of variant hemoglobins can be made in comparison to your electrophoresis. So a large amount of variant hemoglobins you can separate in this case as compared to your electrophoresis. Okay. So coming to the method of how the HPLC works. So first I am just going to make you understand the working of basic HPLC. Okay. So basically remember over here that there is basically a column. Okay. This is the column which is the stationary phase. It is a stationary phase. The column, which is nothing but the silica gel column, this is the stationary phase. Then we are having some buffer, as we can see, the buffer A and B, which is basically providing the your mobile phase. We call it as the mobile phase. Okay. And along with that, we have over here, that is the sample, as we can appreciate over here. So there are three important things of this work. So basically, remember one thing, usually the stationary phase is hydrophobic in nature. Okay, they are hydrophobic in nature, whereas the mobile phase is hydrophilic in nature. Hydrophilic in nature. So remember one thing, that there is a hydrophobic nature of the stationary and there is a hydrophilic nature of the mobile phase. So always remember that whatever sample that I am giving, okay, so for example, I have injected some sample over here. So when the sample is coming, then some amount of buffer is also being coming along with the sample. The sample is nothing but the hemolyzed that we have prepared. Now remember, initially this buffer is containing more amount of water and less amount of organic solvent. So initially the concentration of water is higher as compared to the solvent. So what happens that when the buffer is applied and when the sample is injected, then initially what is happening, the first molecule that is going to come out over here, they are the hydrophilic molecules are going to come out first. Okay, understand this concept very importantly. Initially hydrophilic molecule is going to come out. Okay. Now later on, what is going to happen? Later on, what is going to happen over here in the column, as we can appreciate over here, after all the hydrophilic components come out. So what will happen? Whatever hydrophobic component is there, they will remain over here in the column. Why? Because the column itself is the stationary hydrophobic in nature. So the hydrophobic nature will be present in the column only, that will not come out. So that this column, this hydrophobic material comes out, what we will have to do, we will have to change the concentration of the buffer. So over here, the amount of water is now going to decrease and the amount of organic solvent is now going to increase. So by changing the gradient or the concentration of the buffer, the remaining molecules in the column, the remaining hydrophobic molecules in the column is now going to come out. And this is how all the different molecules inside the sample is going to get separated. Now, how does it work? So whatever sample is now coming, okay, they will be detected by a detector. And that detector is integrated with a computer which is going to display the result. So this is the first part. Okay. So now we are going to understand that how we are getting a particular chart over here. Okay. So this is basically the x axis and the y axis. So basically on the x axis, we are plotting what is called as the retention time. Okay. What is retention time? We will try and understand. Okay. And on the y axis, we have the absorbance in percentage. So as I told you that initially what is going to happen, initially the first thing that we will do as the machine is switched on. So first, initially, before we are applying any amount of sample, we are using the buffer and we are going to equilibrate. Okay, we are going to carry out calibration. So initially only the buffer solution is made to pass through the sample. So initially we will just get what is called as a baseline. Okay, this is the baseline charting we are going to get initially. After this, okay, so this is what you do initially before you run any sample for the day. So this is the baseline you will achieve just with the buffer. Now after that, once the sample is basically injected, okay, so initially, as I told you, initially what did I say? That initially I told you the amount of water is more and amount of organic solvent is less. So initially what will happen, that more amount of hydrophilic material is going to come out initially. So for example, one molecule has come which is going to show a peak like this. Okay. So they have shown a peak like this. Similarly, what is going to happen, that initially after all the hydrophilic material has now come in, now what we are going to do, that in the buffer, we are going to reduce the amount of water and increase the amount of organic solvent. So as a result, what is going to happen, by changing the concentration of this solute inside the buffer solution, now all the hydrophobic material which was stuck with the silica gel, now the hydrophobic material will come on later. And then we will have different types of charts and graphs, okay, like this, for example, of different molecules. So over here, for example, this was molecule number 1, molecule number 2, molecule number 3 and this is molecule number 4. So what has happened over here, that initially the hydrophilic substances came and then later on the hydrophobic substances have come. So let us try and understand that what has happened over here. Okay, let us try and understand and we will interpret. Okay, so basically over here the computer has now integrated and detected each. So molecule 1 has shown this peak and the area under the curve is reflective of the fraction of this molecule M1. Okay, similarly M2 molecule has eluted over here. Okay, eluted means they have separated over here in the graph. Similarly M3 molecule, and the fraction of the molecule is nothing but the area under the peak that I am showing. Similarly the fraction of M4 will be area under the curve. Okay, so this is how. So this is basically how we are seeing each fraction. Now every molecule, for example M1 is having one retention time, M2 is having another retention time, M3 is having M4. So what is this retention time of each molecule? It is the amount of time that each molecule is spending in this solid column, that is in the silica. Okay, that is in the silica gel. Each the amount of time that is spent by each molecule in this solid column, that is called as the retention time. Okay, so this is the basic working of the HPLC. I hope you have understood the basic working. Now we are going to apply this same knowledge over here, okay, when we are going to understand the hemoglobin. So over here the sample, the molecule is nothing but the different types of hemoglobin, and we know that different types of hemoglobin variants or different hemoglobin particles will have different charges, and they are also going to elute separately just as the different kinds of molecules. So over here what is going to happen, over here this hemoglobin is having some charge and they are going to be applied to this stationary phase, that is the silica gel. Now what is going to happen, as we have already discussed, there are two types of buffer. Okay, so as the hemoglobin is going to be injected, okay, they are going to be injected in this particular column, and once they are injected in this column, the separation is going to start because different molecules are having different charges in the silica gel and different molecules among the hemoglobin is having different charges. So there is an ion exchange, and accordingly initially the buffer is having more amount of water and less amount of organic solvent. Okay, so initially again the hydrophilic components will come out. So initially, for example, the HbF will come out first. After that the glycated hemoglobin, okay, HbA1c that is there is going to come out. Okay, so for example I am just going to show over here just a basic chart. I am going to show that how normally our hemoglobin comes. So initially, for example, what is going to happen, we will get a small peak, okay, that is followed by another peak. So this is the HbF peak, for example this is the HbA1c peak. Okay, then after that, okay, what will happen, that initially these hydrophilic components are going to come out and they are going to elute, okay, like the HbF and the HbA1c. Now later on what is going to happen, the hydrophobic molecules, they are going to be retained. Why? Because the column is also hydrophobic and the molecules are also hydrophobic, so they are retained over there. So now what will happen, we are going to change the concentration gradient inside the buffer by making it less amount of water and more amount of organic solvent over here. So over here the organic solvent is, so by changing the concentration of the buffer, now I am going to force the other molecules, the hydrophobic molecules, to come out. So over here, for example, the HbA, A0 that we say, that is the normal HbA. After that the HbA2 will come. Okay, so for example, this is how the different hemoglobin molecules are separated. So these are the normal hemoglobin. Now for example, if any variant hemoglobin is there, for example you have HbS, that is going to elute over here, HbC again is going to elute further on. So different hemoglobin molecules will have different retention times, okay, according to the charges that they have. Okay, so according to their relative positions we can detect them, and we can also quantify by calculating the area under the curve. Okay, so on the x-axis, as I told you, is the retention time, and on the y-axis is the absorbance time. Okay, now in the normal column chromatography, if you see, normally the sample is coming down in the column with the gravitational force, but over here in the HPLC they are coming by using high pressure. That is why we are using the term high pressure liquid chromatography. Okay, and why they are called as high performance, because they have a very high resolution, so they are also called as high performance liquid chromatography. So having understood the concept of the HPLC, now we are going to understand the basic principles of HPLC. Okay, so HPLC, the principle is depending on the interaction of the charged groups on the ion exchange material, that is your silica gel, that is the stationary phase, with with the charged groups present in the hemoglobin molecule. Different hemoglobin molecules will have different charge, so their interaction will be different. So a typical column packing is nothing but it is a 5 microliter spherical silica gel. So as I told you, this is the column packing. This is the stationary phase that I was talking about, wherein the silica gel is applied. Okay, this is the column. So the surface of the support, now remember always this silica gel, always remember initially they are having a very weak positive charge. Always remember they have a weak positive charge, and normal hemoglobin usually they have negative charge, slight negative charges there. Okay, so because we are applying certain weak cationic charge, it is allowing the separation of hemoglobin molecules with different charges by means of ion exchange. So by ion exchange, what is happening, that they are getting separated. The different hemoglobin molecules will get separated because of this ion exchange technique. Now when the hemolyzate, that is nothing but the sample which is containing the mixture of hemoglobin, is adsorbed on the resin, that is in the silica resin, the rate of elution means the rate of separation of different hemoglobin is determined by the pH and the ionic strength of the buffer. As I was telling you initially, the concentration of the molecules inside the buffer will be different because amount of water is more. Later on this will again change. So by changing the concentration of the buffer, different molecules are separated, and then when they will be separated, they will be detected by a detector, and then they will be integrated into the computer, and then a different kind of chart, as we had seen, will be plotted, and then we will see inside the computer. So with the automated system now in use, separation, elution means the separation of the charged molecule is achieved by continuously changing the concentration gradient or the salt gradient of the buffer. So fractions are detected as they are passed through the detector. So as and when, for example, over here initially the HbF variety passed through the detector. So they will be detected by the detector, and then a graph will be plotted for the HbF. So similarly, for all the variants, as they are going to pass through the detector, they are going to have a particular graphing. Okay, they will have a particular chart prepared, and that will be recorded on an integrated computer system which will display the data. So analysis of the area under the absorption peak. So as I told you, if you analyze, for example, HbF, this is the area under the peak. For HbA1c, this is the area. For HbAA, this is the area under the graph. So the area under the graph that you are watching is giving you the fraction of that particular component. Understand? They are giving the fraction of that particular component. Okay. So it is giving the fraction, the percentage of that particular fraction that is detected. Now the time of elution, that is the retention time of any normal or variant hemoglobin is present, is compared with that of the known hemoglobin. Okay, so known hemoglobin is there, so it is already fed in the computer, the fraction time for the normal hemoglobin or the known hemoglobin, and in comparison to that, the variant hemoglobins are also charted over here. So what is the retention time? As I already told you before, the retention time is the time that a particular fraction is spending in the column. That is the retention time. So lesser is the retention time, that means lesser time spent, so they will come first, then someone spend more time, they will come later, then someone spend more time, then someone spend more time. So it is the retention time, is the time that is spent in the column. Okay, so very important thing is we are also being able to quantify both the normal, that is AF, A2, as well as the variant, as we told you, by the method of area under the curve. Okay, so this is the principle of working of the HPLC. I hope you have understood this concept very well. Now as we can appreciate over here, this is the basic charting that is done. So if you see on the x-axis, we are seeing this is the retention time, the time in minute, the time that is spent by each molecule inside your silica gel or in the stationary phase, and on the y-axis is the absorbance, percentage absorbance of that molecule. Over here is the hemoglobin that we are watching. Okay, so as we can see initially, this first graph that we can appreciate, this is a normal person, graph of a normal person, as we can see. So over here normally what is going to happen, this is the HbF that we can appreciate, this is less than 1% in normal, so this is the first graph. The second is HbA1c, okay, that is the glycated hemoglobin. Okay, usually the normal percentage is approximately less than 6.5, 6.5 se normal hota hai, but it is there. Okay, after that majority 95 to 98% we have the HbA, and small amount of HbA2 is there. Okay, small amount of HbA2 is there. A2 is less than 3% in normal individuals. So according to their percentage or the area under the graph, we can appreciate. So this, the number one is the normal adult. This is the normal adult HPLC graph, is somewhat like this. This graph may be asked to you in the exam. Now this is again a normal newborn graph. This is a normal newborn graph. Okay. So over here, as we can appreciate, HbF peak has more, because normally 75% is HbF. If you have seen in the previous lecture, I have spoken about the different types of percentages of different hemoglobin that is present in adults and newborns, and the amount of HbAs are approximately to the tune of 25%. So again, according to their proportion, they are also showing the graph area under the curve is less over here for HbA. So this is how we see the normal graph of the HPLC. Now, as you can appreciate in this graph only, okay, in this graph only, I will show you some important things also. If you see, the retention time of different hemoglobin is given. So for example, the retention time of HbA2 is coinciding with HbE as well as HbE Lepore. So if HbE or Lepore is present, then they are going to elute in this area where the A2 is eluting. And how we will differentiate between the individual forms, that we are going to discuss later on when I will have a dedicated class for the HPLC chart interpretation. But over here, we just have to understand the basic working and basic principle. Okay. Now, along with that, if you see, after HbA2, after this peak, after HbA2, okay, comes another peak, that is the HbD peak. Okay, over here first will come the D peak, then comes the HbS peak, and later on after that comes the HbC peak. So this is how the variant hemoglobin is going to elute. Okay, so I will show you another very important point that you have to understand is the different retention time for different molecules. So as we see there is an F window, HbF window. The retention time is approximately 0.98 to 1.20 minute. Over here, basically the HbF is basically eluting. In the P2 window, just after the HbF, okay, in 1.24 to 1.40 retention time, the HbA1c is going to elute in the P2 window. If it is more than 7%, it is indicative of diabetes, and then we will quantify that as well. Okay. Now we will see the A0 window, which is between 1.90 to 3.10. So over here, basically in the normal, remember over here, the normal hemoglobin, that is the HbA, is eluting at this window normally. Okay, always remember this point. Okay, after that comes the A2. So A2 is at 3.30 to 3.90 is the retention time. So over here the A2 is there. Normally it is less than 3%. Okay, in case of your beta thalassemia trait, it is more than 3.5, up to 7 to 9 is there. But for example, if it is very high to the tune of 20, 25, 30%, then you think about HbE, because HbE is also eluting over there along with Hb Lepore. How do we interpret the individual chart? That will be shown in a separate lecture, but I am just giving you basic idea. Okay. Then we are having what is called as a D window. Now this D window, if you are going to see over here, it comes after the A2, and mainly the HbD Punjab comes over here. Then we have the S window, then that is coming after the D window is the HbS. The elution time is 4.3 to 4.7. Then the HbC window, that is 4.9 to 5.30 as the HbC is coming. So only the ones that I have highlighted, only remember that. Okay, don't have to remember the other form. Okay. Now this is another diagram I am going to show you over here. Over here on the y-axis is the percentage absorbance is there, and on the x-axis we have the retention time. So over here again the same thing, as you can appreciate over here in this graph. So there's a different peaks, different substances are there. So you can see the F, very important, which is eluting at 1.12 over here, as we can appreciate in retention. This is the HbF. Okay, so after the HbF, if you see, will come 1.33 over here. This is the glycated hemoglobin. Okay, this is the HbA1c, the glycated hemoglobin. Then what is this? This is the HbA. What is this? This is the A2, HbA2. After this, what comes? There is the S window, and then comes the C window. Now in between they haven't shown over here, but if D was present, then D would have come just after your the A2 comes the D. Okay, it comes the D over here, as we will see, and along with A2, hemoglobin E or Lepore or even hemoglobin Iran, even they can also come and elute at this particular point in the HPLC. Okay, so I hope this point is very crystal clear to everyone. Okay, so with this we have completed the HPLC. Now we are going to the next investigation, that is called as isoelectric